All right. Hello, everyone. Good evening, good afternoon, and good morning, those in Australia, if you join. Welcome to this VSA webinar, and I'm very glad to invite Stephen Gallant to give a talk. So without any further delay, so the floor is yours, Steve, so please.
Thank you very much, Evgeny. Looks like people say a little bit about themselves at the start of this thing. So for those of you that don't know me, I taught a number of years computer science at Northeastern University, and then worked for a number of companies, and doing a startup now, Textician, for multi-classification modeling, mostly from text, but also from structured data. So without further ado, here's an outline of what we're going to be talking about, sort of a brief, I know this is preaching to the choir, review of VSA, HTC, and MBAT representations. Then we'll talk about a problem with MBAT, the MBAT VSA, and the solution to the problem, which turns out to be orthogonal matrices, which maybe you all already know about, which I didn't know about at the beginning. And then want to talk about using these kinds of techniques to represent JSON structured data. This is a computer science kind of thing that's good for representing complex structured data. And then discuss some points. So vector symbolic architectures, you all know about VSA, also called hyperdimensional computing. Maybe you could leverage the hyper and hyperdimensional computing to get funding for various things, but anyway. So the idea is to represent all objects by fixed length vectors for some fixed dimension n, where typically it might be 300 or 1,000 or more. And what we want is to have similar objects have similar representations as vectors. So similar means that if you take the vector distance, the Euclidean distance, that's small. And the idea is that this is to help machine learning. So if you build a model using some set of examples, and now when you go and apply the model, you see an example where the input is close to one of the training examples. We want that to work well. So that's kind of a main driver for using these high dimensional representations, is to have similar objects come across as similar representations. I'm not going to go over previous work, but I accept to point out that Kleiko and Rachkovsky have an excellent two-part overview of the entire field. It's easily obtainable on arXiv, so I highly recommend that to everybody. Okay, so let's get down to the basics here. So a key fact in this whole area is that vector sums remember their components. And this is counterintuitive. If I tell you I add up a bunch of numbers and I get 137, there's no way of telling whether 15 was one of those numbers. But it's different for vectors. So here we have some examples where the vector for clever is that's column vector, the vector for banker, and so on. Then I have a vector v that's a sum of some of these vectors. So can we tell from this sum which are the vectors that are components in the addition that makes the sum? And the answer is yes, and very easily. We just take the dot product of any vector that we're trying to see whether it's in the sum with v, and if we have a high dot product, then we can be fairly confident that that was one of the vectors in the sum, or a vector close to that was in the sum, okay? we want the close ones to come in there too for machine learning, so we don't have to learn every conceivable small detail for each training example. So another way of looking at it is if we add up a bunch of vectors and we take one of the vectors that's in among the three addends and we take the dot product, it's going to be a high value plus noise. If we take some other vector that's not one of the in this sum, it's just going to be noise. And in previous paper, we showed that the signal to noise ratio increases as the number of dimensions goes up. So there, if you want to see tables with how that varies for various simulations and that analytical thing, you can see that. Now, that's not enough, right? So before I say it's not enough, let me say what else we can get. We can make a sentence vector can be the sum of its term vectors in a sort of bag of words model. So we can just take a vector for each word, and what do we use for vectors for the words? We can use a random vector, but better would be to use something like word2vec or glove or TF-IDF or LSA kinds of things, so that similar words have some similar vectors, and we can just add them up, and we can get very far with that. You know, people say, "Oh, poo-poo, that's just a bag of words," but that's actually quite handy. It works, except in the cases where you need binding. And here's an example where you do need binding. If you have two sentences, the clever researcher saw the large elephant versus the large researcher saw the clever elephant, these have exactly the same words and would give exactly the same vector if just added up. So we need some way to associate parts of the sentence, to bind parts of the sentence. For example, actor role or object role. And we need to be able to represent complex sentences and complex structures. So deeply nested, embedded structures. We sometimes need to have the ability to represent that complex structure. VSAs allow us to do this, and yet still, at the end of the day, we have a single vector representation of some fixed number of dimensions. Okay. So let's talk more about binding, and I'm going to spend most of the time on this one of many ways of doing binding, which I've been working on, called MBAT, standing for Matrix Binding of Additive Terms. And that's the basic paper on that's available on arXiv. So the idea is we're doing binding by multiplying by a random matrix, which essentially takes a vector and casts it into some other space, same dimensional space, but a totally different space. So if we're, for language, for example, if we're doing words in a phrase, we can add the vectors for the words in the phrase, again, giving us a single vector of dimension n once we add them, then multiply this sum vector by the matrix for the type of binding that we're doing, for example, subject or object. And then we can keep on going and add the resulting vector to other vectors in the document. So here is an example, our vectors, so we've got in the entire sentence, we've got everything to the right of this. The actor phrase is the clever researcher, the verb is saw, and the object is the large elephant. So I'm going to use some abbreviated notation here. The vector for a word, I'm just going to put V and then subscript for the word, okay? And for here is a binding matrix, and different binding matrices I'll represent in the subscript which binding matrix it is. These can be randomly generated, at least for now. And that's it. So we can just add these together. So when you multiply by the actor matrix, that puts this vector into sort of the actor space. You can think of it that way. And then when we multiply by the object matrix, it puts it into the object space. So these look different than had you reversed actor and object matrices. And again, so we feel free to add lots of high dimensional vectors, since we can, the vector memory property, we can remember what was added together. So for the MBAT way of doing VSAs, the binding operator has only one argument, which is a single vector. Now that single vector may be the sum of other vectors, which may be sums of, in terms, the results of binding operations and so on. So you can have arbitrarily complex stuff, but the binding operator itself is very simple, and use different matrices for different types of groupings. So the role is subsumed into choosing which binding matrix to use. What you'll mostly see for VSAs is kind of a binary, a two-argument binding operator, where if there's a role, that's the first argument and the operand is the second. But I find it simpler to do complex things using just a sort of a unary binding that takes the single vector, which may have been formed by arbitrarily complex operations, and then just multiplies that by the matrix. Now I should point out that matrix multiplication is non-commutative. Some of other well-known VSA systems have commutative binding, which has its pluses and minuses, and we'll come to that later on in the chat here. So there's a problem. Let's see. Can I stop here and see if there's any quick questions? No. Okay. There's a problem with using random matrices for MBAT VSA. And that is, if you have a complex structure, you end up with lots of matrix multiplications. And if, when we're choosing our random matrices, for example, we make it out of random integers, the multiplications can explode. So one particular case in point is, one way of encoding a sequence is to take a sequence matrix here, and for the first element in the sequence, multiply it by that. For the second element, multiply it by 2 by the matrix times the matrix for the third, and so on. Now the problem is, if we start multiplying these matrices, especially this last one here, this can explode, so that this term will then dominate the other terms for everything that we're doing. Not only dominate, but essentially wipe out the other terms. So that can be a problem. Let me just point out another way of writing this is this sort of this way. So matrix multiplication distributes over vector addition. It doesn't commute, it distributes. But it does distribute. Okay, so how can we get around this problem? Well, it turns out that orthogonal matrices are just the trick. So what is an orthogonal matrix? An orthogonal matrix is, if you look at each column of the matrix, and there's also a version where rows are interchanged with columns, but I'm just going to speak of matrix columns, that if you take and you do the dot product of two columns, dot product is you're essentially multiplying corresponding components and adding them up. I'm leaving out a transpose here, but that's the way we're defining dot product here, where we're using dot product here. That if you take different columns, the dot product is 0, and if you take the same column dot product with itself, you get 1. So these are just the columns form an orthonormal basis. They're mutually orthogonal and have length 1. Okay, so now for a key property that we're interested in is if we multiply a vector by an orthogonal matrix, that its length is preserved. So here's the length of a vector here, which is just the square root of the dot product with itself. The length after you multiply by a matrix is the same as the length of the original vector. Okay, so that means that distances between vectors are preserved also. Here we have two vectors that are bound, that are separately bound, VA and VB. And the distance between these two, you do a little distributed manipulation here, is exactly the same as the distance between the original vectors. So matrix multiplication of a vector just means that you're rotating the vector. And there's plenty of dimension space to rotate. So 2 random rotations are going to be on average roughly orthogonal if you take their dot product. Okay. I'll just quickly go over the idea of the proof. The idea of the proof is that if we look at the squares of the matrix times vector, the length of the matrix times vector, and the square of the original vector, we can show the squares are equal. And since lengths are non-negative, if we show that 2 non-negative numbers are equal, then the original numbers are equal. And you just do it by definitions and sort of follow your nose here. Here's the definition for the squared length, is just multiply the 2 vectors. This is something that I would like to point out, which may not be obvious to everybody. That is, when you multiply a matrix times a vector, the way we're taught to do it is you take row 1 of the matrix, multiply it by the vector. That's the first element. Row 2 times vector, and that's the second element. An equivalent way of doing it is to take each component of the vector, take the corresponding, multiply that, the corresponding column of the matrix, and then sum those up. So if we do matrix times vector this way, the sum of the columns times the corresponding vector component, then it makes the rest of the proof just sort of fall out. You just regroup the terms so that unlike terms are over here, so that they're going to be 0 when you multiply the vectors for unlike terms, and the like terms are going to be 1. So then that you just follow it out, and that does it. So this is so pretty well known among mathematicians and so on, but it's very handy for what we're doing. And this makes repeated binding operations stable and solves our problem. So now if we have MA times matrix A times matrix B times matrix C times the vector, matrix multiplication is not commutative, but it is associative. So that means we can put parentheses anywhere we want, just so long as it's conformable with the dimensions. So we can do it this way. So the length of MC times V is just V by our main property with orthogonal vectors. So this is length V, so then the length of MB times this is also V, so then the length of MA times this is also V. So that means that deeply nested structure with many matrix multiplications are very well behaved. Another handy aspect of orthogonal vectors is that the inverse is just the transpose. So this is sort of obvious because the vectors form an orthogonal basis. If you take the transpose and multiply the two matrices, it's obvious that that gives the identity matrix. But this can be handy for various operations for VSA. Another point is it's easy to generate random orthogonal matrices. You can either do it yourself using Gram-Schmidt elimination, or there's even a Python routine that'll generate a nice orthogonal random matrix for you. Okay, so I'd like to now talk about applying this to something that can generate very complex structures, namely JSON. So JSON is used a lot in computer science, for example, to represent API syntax and that sort of thing. Here's an example from, you all can probably, is this from, what are the Power Rangers or something like that? I'm showing my age here. But in any case, this is from the JSON website. I sort of took out some redundant constructs here. So there's a bunch of name value pairs. So the name is squad name, the value is superhero squad, which is 3 terms here. The hometown's Mexico City and so on. Then the members are an array, not just a single entry. So here's the beginning of the array, and here is the end of the array. So the first one is molecule, first member is molecule man with certain age. He has an array of powers, okay, radiating resistance and so on. The second member is Madame Uppercut, or Madame Uppercut perhaps, who also has age and array of powers and so on. So you can represent arbitrarily complex thing, you know, like the decision trees are a piece of cake, you know, with this JSON representation, which is fairly popular in computer science circles. Here is the JSON definition copied from the website. Uses objects, arrays, and values, where object is an unordered set of name value pairs. An array is an ordered collection of values, and a value can be a string in double quotes, or a number, or the value true, or the value false, or null, or an object, or an array. So, and things can be nested. Okay, so this looks pretty daunting to represent this as a single VSA vector that captures all of the structure in that VSA vector. But if you just do it, it's actually fairly straightforward. So here is our vector here, which is a sum of terms. One term is the squad name. So we bind these vectors for this. And again, a reminder that V sub super means the vector for the term super and so on. And then for the hometown, we get this. And these will be, so squad name and hometown will be mapped into entirely different, unless extremely unlucky, spaces. And here is what questions whether active was true. You have a vector for true, specific vector for true. And then we add to that, and again, we're using the addition property here. We can add bunches of stuff and they'll still be able to operate on their own, so to speak. You can, when you do machine learning, you can represent particular things from particular elements here. So the members are an array, and we'll use this sequence notation for the array. So here's the first element in the array, and here is the second element in the array. So there's two members, and this keeps straight which is which, and they will be mapped into different spaces. So then for the name, here's molecule man. For the age, we'll come back to this, but actually numbers are kind of tricky with VSAs and with JSON. There's kind of underspecified. So we're using kind of a thermometer code here. We're saying that we're having a special vector that says it's a number. And then if the person is older than 15, which is an arbitrary threshold that I selected, we add in that vector. And if the person's older than 25, we also add in that vector. And then we normalize the vectors so that keeps the dimensions intact. We can come back and talk about whether to normalize or not is kind of your choice depending upon what you're trying to do with the vectors. We can come back and talk about that. Secret identity, and then the powers is another array with 3 elements here, and each of those elements is in this case a 2-word phrase, and so on. So that's the first member, and then the second member is this, and anything that, even if it's the same for the first member and the second member, because we're multiplying by M sequence, the sequence binding operator squared, it's going to be mapped into a different space. Okay, these are random projections into this different space. So that's the way we do JSON encodings with MBAT. If you look at in the paper, if you look at the different JSON constructs, it's sort of a direct mapping to MBAT, and most of that we've seen here. So what do we get after we're done, after we go to this work of doing it? Well, what we get is that the final vector, which represents this complex JSON expression, if we use similar terms such as big versus large in this to produce this vector, we'll get similar distributed vector representations. And again, this is very important for machine learning because we don't want to have to learn all possible examples. We want to be able to learn some examples and have it generalized to other cases that are similar to the examples that we've seen, even though we haven't seen those other cases. Not only similar terms with the same representation, but similar representations. So if we make some small structural changes, that will still leave the resulting vectors similar. Again, we're adding together these various terms. So if we add together a bunch of terms and change one of the terms, there'll still be a good amount of similarity in there. One thing to note, it's important here. So some of these terms can get pretty convoluted here. So here, if you look back at the example, one of the terms has these 6 binding operators, binding matrices multiplied together times radiation. So this is where it's important that length is preserved. So once we multiply these 6 matrices times this vector, the resulting vector will have exactly the same length as just the original vector, v radiation. So the resulting vector is just a rotation of the original vector. Okay. So it greatly simplifies everything by having this orthogonal matrices multiplying a vector preserve the length. Another important thing I'd like to point out is that matrix multiplication being non-commutative can be a feature and not a bug, okay? So in particular, one of the terms that we get, if we go back, if we shift one of these M sequence operators from one place to another, I think it was originally, we can go back and look at it, but point is that this was something that was, oh, it's from here. Here, if we shift, here, we've got 3 M sequences. If we shift one of them to here, that will give us different place in the structure. That would place radiation as the second power of atom uppercut rather than the third power of molecule man. So if we're trying to represent structure, it's important that the binding be non-commutative, or else we're going to have a very hard time representing complex structures, such as in this example. So, period. So I think we want binding to be non-commutative to represent complex structure. And let's see, I had a correspondence with Tony Plate, and he agrees with that. And for his VSA, he thinks that permutations should be used in order to make it non-complex. So I'd like to talk a little bit about numbers here. So numbers are surprisingly tricky with VSAs. You know, that's sort of bread and butter. We use them all the time. There's at least 3 types of numbers. One are IDs. So ID 1000 is totally different than ID 1001. And if we want to encode these, we can do them as unique words, so that 1000 is a unique word from 1001. Then there's continuous numbers, which we can do by putting in some marker that it's a number, and then have various thresholds where if it exceeds the thresholds, you put indications that it exceeded that threshold, like very low threshold, high threshold, and so on. So this is what Bernie Woodrow used to call a thermometer code. Is one way to encode this. There's other ways to do these continuous numbers, but the continuous numbers, when you think about it, are really quite different than IDs, even though if you just see one of them, they may look the same. And then there's other cases like zip codes, where if the 92 is in common, we want that to be kind of close, and so on. And I'm not going to go into ways of doing that, but there's kinds of sequence coding that you can use to encode zip codes. Okay, so now let's discuss some of these other topics here. Limitations, when VSAs don't help. Suppose you were trying to encode medical records. Particularly, we're focused on notes from physicians and nurses and so on. There's a single field that, so there's the text, and then there's a list of prescription drugs that for this particular stay. We can encode the prescriptions as a VSA, you know, bind them together as a VSA. But if there's only one set of prescriptions, one kind of prescriptions for each person's visit to the ICU, that may not help. I mean, we've seen cases where instead of using the VSA and binding matrices and so on, you're better just to add the prescriptions as text at the end of the text for the patient record. And that's simpler, and we're actually getting better results by doing that. So if there's only one kind of prescriptions, then you might as well just consider the prescriptions as text and add them in. If there are 2 kinds of prescriptions, then we need some sort of VSA stuff to keep them separate. So if there were prescriptions before the patient entered the ICU and then new prescriptions for after the patient entered the ICU, and we want to keep those straight in our modeling, then we need some sort of VSA binding to keep them straight. Second point is that we think VSAs are ready to try with real world problems in lots of different areas. Like genomics, it would seem natural to bind together various regions and use the binding matrix to specify the type of annotation for those regions and so on. There, you know, as well as medical records and that sort of thing. Finally, not quite finally, we can see machine learning is doing kind of a progression from using just numbers to using text, you know, BERT and all that sort of stuff. And now we can also use structured data, which would have been hard without VSA kinds of approaches. So that's it. I'd be happy to take any questions.
Thank you, Steve. So now we have time for questions. Please unmute yourself and speak up.
Hi, Steve. This is Fritz. I have actually two questions or two comments, and one concerns the encoding of numbers. Have you looked into using actually fractional power encoding for this? And there you can actually also make a transition from, you know, more like an index number where it really matters if there is a difference of an integer of 1 versus something that blends more in. That might be another natural way how to actually encode numbers. And the second question is, I mean, we analyze kind of liquid state networks and reservoir computing with VSA methods. And we, of course, also encountered the orthogonal matrices. But in this case, it's just one orthogonal matrix. And you basically encode an input sequence with that. But I realize now this is very similar to MBAT. The only difference in MBAT, you can have many different matrices for all these, you know, the different things you want to encode. And in echo state networks, we often also use orthogonal matrices, but rescaled by a lambda which is smaller than 1. If you want actually to encode some data streams, and this then allows you to actually forget older stuff slowly, so your vector norms now shrink. And so you could do a similar thing with MBATs, but in a more complicated way than in these echo state machines, by using these many matrices for the different things you want to actually bind. I'm just wondering whether you thought into this direction.
So I'm only a little familiar with this stuff. By fractional encoding, are you, for example, talking about two vectors and fractionally mixing them in order to represent?
Basically an exponentiation. Let's say you have a complex vector with phasors as the individual entries, and now you just rotate the phases by a certain you know, by a certain number, and this encodes, this then forms vectors. Another vector, this kind of base vector to the value forms then a VSA vector that encodes that number. And now, of course, it depends on how quickly the exponent changes. So if two numbers are entirely different, then the vectors are pseudo-orthogonal. And if the exponents are close, then the two representations are quite related. So you get these kind of kernels where you know, if two numbers are very similar, then the similarity of the vectors or the inner product is quite high. And then as the distance of the two numbers increases, it kind of becomes, the inner product gets near to 0. Yeah.
Yeah, that's it.
Yeah, and so I mean, there's this. So so this is kind of some people call this semantic pointers. In Elias Smith group, and we recently wrote a paper where we also showed how this actually connects to kernel methods, and the paper has in the title Vector Function Architectures. It's a 2021 paper, I think.
Yeah, sounds interesting. Something similar that we did with Phil Culleton was actually have similar matrices and have them parameterized. We did this for image processing example, where the matrix was parameterized, and you have continuously vary from one matrix to another to express certain positions, image processing positions, and so on. But
I'm not familiar with that. Yeah, so if you have a pointer, please.
Yeah, I think it's on archive, or if you drop me an email, I'll be happy to send it to you or whatever. But
thank you. Yeah.
Sure. Thank you, Fritz.
More questions?
Hi, Stephen. It's Dennis speaking. We're a number of people here at Redwood Center listening to your presentation. Thanks for the presentation. And I was curious, was there any plans on your side to apply this idea within your startup? Because that would be curious to see how, like, what kind of applications can be addressed with this idea of a JSON, because that's not to me. It's clear that it might be very useful for machine learning models, because for any variable structure we're gonna get a single same size vector representation. But have you done any like preliminary experiments that you can talk about?
So JSON is an example that you can do complex structures. So we are hopefully going to try and get mimic medical database, all or part of it, into vectors using these methods. And then you can build predictive models for whatever, predict whether a disease is going to occur or so on, or whether the patient is going to be returned to the ICU frequently, or that sort of thing. And anything you can think of, once you have a target field and you have the medical database in terms of these VSA MBAT vectors. So we're hoping to do that project, but we're in the earliest stages of it. We have it partially done now, and we're looking at text and some structured data.
Great. Thanks for clarifications.
Yeah. I can.
Enter, please.
Well, I have a comment about orthogonal matrices, and I certainly believe in them and use them in my work, but in a simplified form, and that is as permutations. Permutation matrices I think they satisfy all those same conditions.
They are orthogonal matrices.
Right. And whereas if you have n for the matrix, you need n squared numbers. For permutation, you n times log n will capture them. So permutations, you may be able to do everything with where you now use general orthogonal matrices. You may be able to do it with permutations.
You can do a lot. You can point to cases where you're better to not use permutation matrix. And I'll tell you one. If you take the high dimensional version of the old exclusive OR problem, where you have, say, a 100-dimensional vector where if it's +1, it's true. If it's +1, -1, and then a bunch of zeros, the rest are zeros, it's false, and so on. So if you now do a permutation of any of those vectors, it still will be non-separable because you'll only be shifting, there's only 2 pieces of the vector that really count, the first 2 components, the rest are all 0. Whereas if you do a more general orthogonal matrix, almost any one you pick at random, with extremely high probability, will then be separable because you'll be mapping it into a space where those 2 non-zero dimensions suddenly become lots of non-zero dimensions. But in general, I certainly agree that permutation matrices are orthogonal matrices, a huge but finite set of orthogonal matrices. Yeah.
And the other thing, this is Tony, are you there? Tony also talks in his book, or in a dissertation, about these fractional powers, and those applied to holographic reduced representations. So the fractional powers, I think they give you more like continuous numbers.
And as a way to represent continuous numbers, you mean?
No, I think Tony would have to speak to that if he's still there.
Yeah. The fractional powers, they give you a way, if you have very similar numbers, then you'll get similar vectors for them, and you can change how fast the exponent varies. So it's a way that if you can make, like, the numbers 999, 1000, 1001 can all be close to each other, but still slightly different, and there'll be a lot more. They'll be closer to each other than they are to 900 or 800, but
that could be a better way.
Yeah, I think that for numbers, it's gonna totally, I think, like you were saying, it totally depends upon the application. What sort of similarity structure do you want your numbers to have?
I have a question. Just follow up this discussion. How this HRR representations, like fractional powers in real numbers, is compatible with this squared matrices binding, because that representation of number that you're talking about, so they require different kind of binding operation, which is convolution. So are they compatible with MBAT? I don't, at least I don't see directly how.
To me, it's very similar. Because the convolution is just a matrix multiplication.
Yeah, that's true. Yeah.
So the matrix is more general.
Yeah. I also think, you can define fractional power encoding with MBATs by exponentiating the matrix and just using, an expansion of that. So you can. It's very similar to exponentiating a vector. I think you could define it in a similar way.
Mm-hmm. Now, will it be reversible? So can you go back to? Can you unbind in MBAT?
In MBAT? Well, there's
how can you unbind a vector in this architecture?
So you can multiply by the inverse, which is
you multiply it by inverse, which is
the
a transpose. Yes, of course.
Yeah.
Yes.
Yeah. So.
I also have a question, kind of following up what Dennis asked, more on the application side. So what kind of problems you have in mind to solve? Is it more of kind of similarity matching between records, or really finding one record that contains certain specific parts? So, I mean,
So machine learning inputs, for training, for trying to predict various things. I'm thinking you can take complex structures and use them to train classifiers, for example, even though the structures are very complex. You can also do search. You can do similarity search. Is another kind of application.
Yeah, I'm more into, I mean, to which extent MBAT is kind of better or stronger compared to this kind of traditional bindings, like vector by vector, because I mean, we did some experiments with machine learning and representation of structured data with just VSAs. I mean, classical binding, I mean, depending on representations implemented in different ways. And so you can encode quite large structures. So of course you lose the ability to go back to atomic vectors, but it's very useful for inputting this. I mean, to use it as input to machine learning methods. So that's true. But would MBAT add something something extra to this task, or will it result in a higher accuracy, or where do we see the gain?
Well, if it allows you to do more complex structures, and complex structures can cause problems with some ways of doing VSAs, deeply embedded structures, for example.
But it would be interesting to see some comparison, like in terms of accuracy on different using different machine learning or neural networks. So
yeah. Yep, I agree. Yeah, you have to.
It just came to my mind. I understand where a possible gain can be, but at least I didn't see yet the kind of comparison between different on a given set of tasks.
Yeah, I agree. That would be pretty interesting.
All right. Any more questions? All right. Well,
I just want to say one more thing.
Sure. Go on.
Steve was very early on into semantic vectors. And that's when I first sort of got to know about your work. And that really goes back into what, 1980s, 1990s?
Somewhere back there.
Latent semantic analysis. I think it was, and I think it's still used in cognitive science.
Right. Well, that was Sue Dumais and Deerwester and so on. But it was about the same time,
Yeah.
And I did a paper with them, with Susan Dumais too.
Right.
But yeah, I originally got started with what I called context vectors, which were high dimensional vector representations for terms, and with adding up the term vectors. So, and that was for document retrieval in those days. So
This high dimensional vectors, they go back a long ways.
yeah. So and your stuff goes back further than that. I remember hearing a talk that you gave back when I was first starting this stuff. But I know it was some company was sponsoring you or something, but that goes way back. So
Right.
All right. So if you come up with new questions, then please feel free to use our mailing list as usually. So and write to Steve directly.
Right.
And well, from my side, I want to thank you once again, Steve, for joining us and giving this excellent talk.
I'd like to thank you, Evgeny, for inviting me and for everybody for coming and providing all these interesting questions and so on, and doing the work you've been doing. So.
Hey, yeah, thanks, Steve. Hey, I just want to make one final comment. So somebody you mentioned was asking about applications. So yeah, I think for all of this work that various of us have been trying, to me the applications are key, because I see so much. There's, you know, for the last couple of years, the dominant paradigm has been throwing everything into large language models, into transformer models, and people are doing a ton of really interesting stuff and getting lots of results out, you know, amazing performance, but they are still missing elements of structure. There's like all these hallucinations, and if we could combine these things, that's where I think we could make progress. But that's the challenge, how to combine these things.
Yeah, very interesting. Yeah, I would try and combine, have your VSA and your huge numbers of weights too.
Yeah. The VSAs or the MBATs or whatever scheme, they all have a ton in common. They give us a way of understanding the structure that's there, and then how can we use the large networks to manipulate it.
Yeah, thanks, Tony.
All right, thank you all. Thank you all for coming. So I'll see you in 2 weeks. So don't forget, in 2 weeks' time. So come back to new VSA Online seminar. Thank you all. Have a good day.
Bye-bye. Thanks.
Thanks. You
Bye.
too.
Thank you.
Thanks.